Hi everyone, this is Mr. Dubrow. Before we get into our course, we may want to take a few minutes to review some properties of vectors, including vector operations and vector components. So we're going to do that in a couple of videos here. And in this first video, we're going to focus on reviewing components of vectors. So we're trying to figure out, first of all, what is a vector and what does it represent? And how do we mathematically combine them? So first of all, a scalar is a quantity that just has magnitude, such as distance, speed, time, or mass. A vector, on the other hand, has both a magnitude and a direction. So quantities such as displacement, velocity, and acceleration are all vectors. Now vectors are described as having a tail and a head. And we usually write a vector with a letter that has an arrow above it. And sometimes in a physics book, you'll see it in boldface or bold type. But sometimes it's hard for us to draw that, so I'll do my best to always put an arrow above a vector. We can denote the direction of a vector by the direction that the ray points. And this is usually an angle measured from the positive x-axis. So we can measure that in radians or degrees. Sometimes we talk about vector direction using unit vectors. Now the magnitude of a vector is the size of whatever the vector represents. So if I said that I'm going, for example, with a velocity of 50 miles per hour and the direction is north, well then the entire vector would be both 50 miles per hour and the direction would be north. But the magnitude of that would just be 50 miles per hour, the length of that vector. And to show this symbolically, we often put bars around it. And I'm not sure why B is in a box, but that would be the magnitude of A. So vector A is 3 miles to the north, then vector B would be 6 miles to the north. Equal vectors have the same length and direction. They don't have to be in the same place, but you should be able to translate one to the location of the other. So all of these are equal vectors. Inverse vectors have the same length, but in the opposite direction. Okay, so another way to think about this is that if I take vector A and if I add to it its opposite, I should get back to where I begin. I should have 0. Because of course, vector A has to be equal to itself. So if I subtract it to the other side, I get A minus A equals 0. And this is where we can come up with the fact that if I start here and go A, and then I come back negative A, I begin and end in the same place. Okay, so graphically, there's a couple of ways to add vectors. The easiest way to do this is called head to tail. So this means that the head of vector A is going to be lined up with the tail of B. So the tail of B is right there, and the head of A is right there. And when we add them up, the sum of these is called the resultant, R. Now the inverse of the sum, also known as negative R, is called the equilibrant. And one way to see this is that if A plus B equals R, then A plus B plus the opposite of R must equal 0. And that is what we call the equilibrant, is the opposite vector to R. Okay, so that just shows that A plus B is equal to R. Okay, now we can also combine vectors using components. So we can take each vector and resolve it into its x and y components. So if I have a vector A right here at an angle theta, then I can have AX and AY with the following components, that AX is a cosine theta and AY is a sine theta. And we can do this for a series of vectors a, b, c, etc. We would then add all the x components to get Rx, the resultant in the x direction, and we do the same thing with the y components to get Ry, the sum of the vector components in the y direction. We would use the Pythagorean theorem to get the magnitude of the result and use an inverse tangent function to get the angle. So as a quick example, let's say we have these three vectors and we want to add them graphically and by component. So first of all, it's a good idea to set up a table of values for the x and y components. So we can take a and b and also c and break them up into components, okay? So it's probably best to sort of sketch this out. So this is going to be vector A, and we'll do this more carefully on the next slide, but that's at 60 degrees. Vector B at 100 degrees will be kind of like this, because that's going to be 90 plus 10. And vector C at negative 120 will be something like this. Okay. And actually, if we think about it, the negative 120 will be going diametrically opposite to the 60. Okay, so then we think about components. And so vector A is going to have a positive x component. It'll be 300 cosine of 60, which gives us positive 150. And we usually say that up is positive and to the right is positive, or the traditional xy axes are positive. And for y, we will get about 260 by doing 300 sine of 60 degrees. Similarly for vector B, which is right here, we're going to get a negative 78.1 and 443 for y. And for vector C, we're going to get negative 60 and negative 104. Okay, then we're going to get our result, and we're going to get our Rx is going to end up in this box, and this is going to be Ry, because this will be vector R. And so this is going to give us about 11.9 and 599. So what we do with that is we create a new vector that goes about 11.9 this way, and then this is totally not to scale, but about 600 that way, and these are meters. So I should be putting units on these, or I could just say x is in meters and y is in meters. Okay. And then we would use the Pythagorean theorem to determine the hypotenuse. And this is this is only 599. Okay. And so the hypotenuse here is going to be about 600 or so, a little bit more than 599, and it's going to be at 88.9 degrees. Well, we could say that's north of east. Okay. And so if I have east, north of east is going this way, 88.9 degrees. And just graphically speaking, we can add them as if we start at a particular point right here. Remember, vector A was about 300, and so I won't do this perfectly, but at 60 degrees, maybe we go something like this for vector A. Vector B was about 450, going kind of like in this direction. Oh, I'm sorry. Vector B is actually going the other way. So A is going to be going kind of like this. B is going to be going, remember, at about 100 degrees. And C is going to go kind of down like this. And I didn't do my magnitudes very well. A should be a little bit longer in comparison to B. So kind of like this. And so the result should give me something that goes kind of like this. That's almost 90 degrees. There's my result. Okay, so that's how I would add them graphically. All right, so in the next video, we'll talk a little bit about the dot and cross product.